Okay, welcome to Econ 403. I'm now talking to you a little bit about homework set 5, which is due on next class, next Tuesday. So the first one you should be more than capable of solving because it is an optimization problem or a maximization problem with three choice variables. Now you haven't seen one with three choice, you've seen one with three choice variables, but you haven't had one on a homework or quiz yet. So the good news is I'm not asking you about the second order conditions here because I didn't teach you the second order conditions for three choice variables. So why would I ask you to do it? Here's another person is coming. But I do want you to find what I call a potential solution. Oh, another person. Okay, we're coming. People are coming. Okay, so for number one on homework set 5, I would like you to write out the first order conditions for this maximization problem to find a potential solution. And I actually want you to find the potential solution. So you'll have a first order condition for X, first order condition for Y, a first order condition for Z. That's 3 equations. And each equation is going to have possibly an X and a Y and a Z in it. It depends on the derivatives, but as you'll see here, there will be X, Y's, and Z's in those 3 equations in various components. Then you just have to solve a system of linear equations. I think it's going to be linear. Huge hint here. This is just going to be a system of linear equations that you have to solve. And you can either use Cramer's rule to solve it, if you feel like it, or you could use substitution to solve it. You can use a calculator. If you just use something like an equation solver, I'm sure those exist. I would still rather you give me some information about how you would do this problem. What am I saying? I guess I would like to see some work that you show here, either with substitution or with Cramer's rule, but you can use calculators to sort of simplify the problem for you. Like, for example, if you want to calculate a determinant, I'm okay with you just plugging it into a determinant calculator. I do the math yourself. It's not that hard to do your math, but you can even check it with the calculator. I'm totally fine with that. But just show a little bit of work that would show me that you would know how to do something like this. But please use a calculator, even if it's like a determinant calculator. Okay, that's what you have to do for number 1. How about number 2? This is the method of Lagrange multipliers, which I asked you last class if anybody's had this before, if you're familiar with this process, this method. I'm not sure anybody said they were, which means you never really came across it in another class where you had to use it. But for my class, I think you do have to use it. I think there will be enough problems that kind of look like this, or even more complicated than this, where you'll have to use it. And so I want you to learn it. And once again, I'm not asking you to show the second order conditions here, even though they do exist. For a problem like this, there's like a different type of second order condition. I wasn't even sure if I would get to that today in class. So if I don't get to it today, then I didn't want it to be on the homework. So that's why you just have to write out the equation, find the first order conditions, use the first order conditions, solve for any potential maximum. Okay, so I think you're good on 1. Let me know if anybody has like a question about 1, like how they think they might get stuck if they tried to do 1. You think you can finish number 1? If that's the case, then don't ask me a question. But for number 2, I need to teach you this method. I think we're ready to do that now. I'm okay to share this. I'm a little nervous sharing something that I'm looking at for the first time. Where is my course documents? I'm just going to go back to the same PDF I had before. Lagrange multipliers and constrained optimization. We got through a lot of it last class, but we stopped right at the juicy part. Here we go. I will share this with you. Share screen. Excuse me. Okay, I gotta review here. I gotta remind you of the problem. The problem was a budget constraint, utility maximization problem that sort of looked like this, but mathematically it looked like this. Let's maximize over any choice of f or s this objective function. The objective function is f times s. That's what we're trying to maximize, such that this is a constraint now. F plus s must be equal to m. However much food or shelter you purchase, the total of those has to be equal to your total money, m. Okay, so that's the consumer choice problem. I showed you one way to do it using economics and the implicit function theorem. A second way to do it using substitution, just like eliminate f from the problem, in which case it becomes a lot easier. And now here's the third way, which is, I think, the most important way for you to learn for the class. But before we talk about that, let me just say what a Lagrange multiplier is. Why is it called a multiplier? Is it like a multiplier effect in macroeconomics? Actually, no, it's not like that. Don't think of it like that. A multiplier is actually, it's a variable. It's a variable which will be multiplied by something. I think maybe that's why it's called a multiplier. But fundamentally, it is a variable. It is a variable which is called lambda, I think because lambda is Greek for L, which is the first name of the guy who invented this method, Lagrange. And this variable lambda does not exist fundamentally in the problem. Our example right now that we're, method 1 and 2 that we went through yesterday, last class, was budget constrained maximization problem. There's nothing in there about lambda. This Lagrange multiplier isn't really, a real variable, any sort of real choice variable. That's not why it's there. It's actually created by us, the person doing the problem. It's created solely for the purpose of doing constrained optimization. It's like a helper variable. You create this variable lambda knowing that it may or may not have some sort of economic meaning. Sometimes it does have some economic meaning, but it certainly doesn't have any sort of real world sort of choice component to it. Nobody's choosing lambda. We're simply creating lambda in order to solve a problem. Okay, so that's what lambda is, a variable. What do we do with lambda? Well, we take lambda, this variable, and we multiply it, thus the name multiplier. We multiply it by the constraint, where you might say, how can you multiply a variable times a constraint? Because a constraint is an equation or an inequality, one of the two, but the way you do this is by writing the expression of the constraint in such a way that it's always equal to 0. We did this before with the implicit function theorem, or rather just implicit functions. You could see an implicit function, which is an equation with stuff on both sides. Every single time you see something like that, it's trivial to just move every term to the left side of the equation, and that left side will be equal to 0. Well, do the same thing here for a constraint. Somebody gives you a constraint like f plus s equals m. You can always turn that into something which is equal to 0 by moving things to the left side of the equation. That would be f plus s minus m equals 0. So that's what you're going to do. Maybe that's the first step, actually, of using Lagrange multipliers. The first step is to write the constraint as an expression which is equal to 0. You can always do that. Okay. What do you do after that? You take your newly created variable lambda and you multiply it by this expression, the left-hand side that you get when that's equal to 0. Okay, so it's lambda times the constraint is added to the objective function. And this is called the Lagrangian function. So this method of Lagrange multipliers, it has a Lagrange multiplier, which is a variable lambda. It also has a Lagrangian function, which is equal to the objective function plus the multiplier times the constraint. So that's what I want you guys to know, internalize, and be comfortable with. The Lagrangian function equals the objective function plus the multiplier times the constraint. So you have this new function that you've created. It's called the Lagrangian function. So what? What do you do with it? Well, you optimize it. You optimize it in a way that's pretty much the same way that you would normally optimize a function. There's only a few little differences, and I can talk about those in a bit, but pretty much you're trying to maximize. If it's a maximization problem, you're trying to maximize the Lagrangian function. If it is a minimization problem, you're trying to minimize the Lagrangian function. The key is going to be in the fact that you've internalized this constraint now. Whatever your constraint was, you've written it as an equation which is equal to 0, and you've added that to the function. So it really shouldn't change the value of the Lagrangian function, right? Here, let me say that in a different way. The value of the Lagrangian function is equal to the value of the objective function. Wouldn't you agree? I kind of hope that anyone who's paying attention would understand this, because the Lagrangian function, I need to annotate. I'm so used to annotating now. I don't know, maybe I like to annotate. This function here, the Lagrangian function, it's exactly equal to, in terms of the numeric value, it's equal to the objective function. How do I know that? Well, because it's actually equal to the, what I'm going to abbreviate here, objective function plus the Lagrange multiplier times the constraint. But remember, the constraint is always equal to 0. So in this case, you have the objective function plus something times 0. That's just exactly equal to the objective function in terms of the value. In terms of the variables that are inside of it, it's actually not quite the same. Here's why it's not quite the same functionally, is because you're allowing your choice variables to be anything they want to be in the Lagrangian function. So you're not sort of assuming that the constraint has held. You see that difference? Using this method of Lagrange multipliers, you're almost like, let's consider that we weren't constrained with our choice variables. So we could pick any choice variables we want. We can think of it that way and maximize the Lagrangian function and get an answer to our original question, which was a constrained optimization problem. This is what we're actually doing. We're doing a constrained optimization problem, but we're sort of rephrasing it, rethinking it as a maximizing this weird thing here, the Lagrangian function, and in an unconstrained way. Like, oh, what if this is unconstrained? I can pick any choice variables I want. And I'm really maximizing this thing called the Lagrangian function. It'll give me the same answer as if I were solving this original constrained optimization problem. And that's the key to this method. You guys have any questions about that? I think my nose is because of the pollen. I have a lot of pollen where I live. No questions about this? You want to see some examples, I bet. You'd be fools if you didn't want to see any examples. I would question your interest in learning this in the first place if you're like, nope, don't need to see any examples. Okay, let's see what it would be like to set up a Lagrangian function in our case. This is the case of the very, very simple consumer maximization problem. Remember, the constraint is S plus F equals M. Let's just rewrite this You might say, why did I choose m minus s minus f equals 0 instead of s plus f minus m equals 0? I would argue that doesn't matter. It's the same thing. One's multiplied by -1, but 0 times -1 is 0, so who cares? But I will say this, there is a convention. You know what conventions are, things that you do not because you have to do them, but just because everyone does them, and it looks nice when you do it, when you follow the convention. The convention is to take the right side, make it positive, and subtract the left side. And the reason, there actually is a reason for this convention. And that is because in the future, we'll talk about cases where instead of being an equality, the constraint isn't just an equation, but it's an inequality like this. S plus F is less than or equal to M. In that case, it actually does matter how you write which side minus which. You should always write it so that the bigger side is the positive one, and you're subtracting off the smaller side. So why did I write it as m minus s minus f equals 0? It's because it's a convention. Most inequalities are written so that the left side is less than or equal to the right side. They're not always written that way, but most of the time they're written that way. And that means if I want the bigger thing to be subtracted by the bigger thing minus the smaller thing, that means I need to take the right side minus the left side. And that's why I've written it this way. Sorry for all of this time. I've just been explaining this convention. I won't count it wrong. If you wrote it s plus f minus m equals 0, it would not be wrong in this case. However, later, it will potentially lead you to a wrong answer if you don't get used to this way of writing it. So it's the right side minus the left side. Okay, assuming it's a less than or equal to sign. If it were for some reason the other way, then you would write it the left side minus the right side. Okay, that's enough. Clear all drawings. Okay, so right now we're just setting up the Lagrangian function, which remember was part A of the homework I asked you. I asked you to do only 2 problems for the homework. The first one I think is pretty easy. The second one I think is pretty easy too. The part A of homework problem 2 is just to write the Lagrangian function. Okay. Did I call it a function or an equation? I meant function, but maybe I said equation. I'm kind of curious if I made that mistake, sort of when I'm talking. Yeah, I called it an equation. I meant function. I think it's not really an equation. It's the function. Sorry about that. I don't think that's too ambiguous what I mean. What I want you to write is this. The Lagrangian of this, remember we're going back to our example of, do I need to write, oh, it's up here. Oh, it's actually way up here, sorry. Here's the problem. Max f comma s of the objective function, which is fs, such that is our English way of saying what follows is a constraint, right? So mathematically, you will see this written out often, either max or min, and then the choice variables will be described underneath. Sometimes they have an additional constraint here. You might say f comma s greater than or equal to 0 or less than something. That's okay. You can make some restriction on f and s underneath the max sign. Then what follows that is the objective function, the thing you're trying to maximize. Then you'll see such that, or sometimes just s period t period, which is an abbreviation for such that. That's how it's written sometimes. And then what follows that is the constraint. You're not allowed to just pick any f and any s. You have to pick an f and s that satisfies this constraint. And the constraint could either be an equation that holds with equality or an inequality. That's okay too. Right now, we're talking about a constraint that holds with equality. and a very simple objective function, and no restrictions here on f and s, which I think maybe is a mistake. No, it's okay. That's fine in this case. All right, so let's write the Lagrangian for that. If I'm going to stay on this slide and write it. What would it look like? L for Lagrangian is equal to what? Someone tell me. I'm sorry if I'm going slow. I'm going slow because some of you said you've never seen this before, and just want to make sure everyone gets it. What should L be? Oh, good, Kai. What are you gonna say?
F times S.
Good.
Plus.
Good.
The multiplier.
Which is lambda. Very good.
Yeah.
Do you use the Greek letter sometimes? Lowercase lambda?
Lowercase lambda. Okay.
I mean, you don't have to call it lowercase lambda, but it's a lowercase. I think uppercase looks kind of like this or something, but lowercase looks like that. If you're familiar with Greek, fraternities, sororities, you probably see the capital lambda more than the lowercase.
Yeah, I'm not familiar, but parentheses.
Parentheses, good.
M minus S minus F. Good.
You got it exactly right. If you did this on your homework, I would give you full credit. And that is a perfect description of the Lagrangian function. Everyone see how she got that? L equals the objective function, that's that, plus the multiplier times the constraint. She even followed the convention of writing the right side minus the left side. I even like that. It would be fine the other way, but I like it. I like it better this way. Okay, good job. That's like part A of this problem, and we did it. I'm going to clear my drawings. I gotta clear out my tool and go to where I was. Setting up Lagrangian function. Yeah, it's also written right here. We got the same one. Now let's look at the first order conditions of Lagrangian. Well, as you might expect, in this case, they're exactly the same. Only there's one for each choice variable, and there's also one for the multiplier. So in this case, there are 3 first order conditions, one for f, one for s, and one for lambda. M, if you recall, is just an exogenous variable. It's like a parameter, so don't worry about it. Treat it like a number. But for f, s, and lambda, there should be a first order condition. So let's write them out. The first order condition for this Lagrangian function are going to be the partial derivatives of it, which will then be set to 0. So the first order condition, the one for f, is what? The derivative of f times s with respect to f is s. Okay, now I'm kind of looking, I'm scanning here to see any other f's that appear. Yes, here's an f that appears. How does this f exist? It's being multiplied by -1 and by lambda. So the derivative, the partial derivative of this with respect to f is actually negative lambda. That's why it's s minus lambda. I set that equal to 0 because that's what all first order conditions are. They're set equal to 0. Okay, that's my first FOC. The second FOC is do the same thing, but with s. F times s becomes f because f is the constant that's being multiplied by s. And same thing here. I'm scanning for s's. I see an s here. There's a lambda, -1. That's why it's negative lambda equals 0. Now that's the second order condition. How about the third first order condition? Well, that's with respect to the multiplier. And the derivative of this with respect to the multiplier is actually, there's nothing here. There is something here, and it kind of gives you back the constraint, m minus s minus f equals 0. So this third first order condition is kind of special because it always gives you back whatever constraint you put into it. So that's why that's kind of maybe a glimpse into why this works. It's really not so complicated, actually. It's like, well, do your normal first order condition for f and s, and you get the constraint back, and you're going to solve all of this. But there's just one little extra thing here, which is that however s and f exist inside the constraint is going to also appear in the first order condition, and it wouldn't normally. So if you ignored this minus lambda, you would get the wrong answer here. If you sort of ignored a constraint and just maximized the function, and then afterwards said, okay, now let's see what it's like once I add the constraint, that wouldn't be a very good method, because there are some trade-offs that could be inherent in the constraint that you're ignoring. Okay, but do you see how this is the answer to like part B? Part B of the homework says find the first order conditions. You're going to find one for, I think I have it. I really hope this is okay. Yep, I think I'm just switching here. So for this problem, homework set 5, problem 2, part A, write the Lagrangian equation. It really should say Lagrangian function, but you know what I mean. I guess it's an equation if you say L equals blank. That's the equation. L equals this objective function, right? Minus lambda times this constraint written right side minus left side. That's it. That's the answer to A. Find the first order conditions. You're simply going to take the partial derivatives of that, what you got from part A, with respect to x, y, and lambda. That'll get you the answer for part B. How about for part C? I'm not even asking you to, like come to a complete final stop answer to this problem. I really just want you to find any potential maximum, and those are the ones that satisfy simultaneously the set of first order conditions. So you just, at this point, you're all just solving a system of equations, just like you did in part 1, but you're going to solve a system of 3 equations. Lambda should be pretty easy to eliminate from your system of equations. So I actually don't recommend using Cramer's rule. You won't be able to use Cramer's rule in general, unless everything's linear. But you can solve it with a substitution. That's what I recommend. Find some way to substitute and eliminate variables using substitution to solve the system of equations. That's what I recommend for you on part C. And that's it. That's all you have to do for this homework. I know I haven't given an example of this, but we'll do it later. But do you guys have any questions about what's expected of you from this homework? Let me know if you do. You can be private. Okay, let's go back.
Wait,
sure.
We're only for part C. We're trying to find, like, when we use substitution, we're trying to find x and y, right?
That's correct. Now you can find lambda also if you want. And actually, I know that in the book, sometimes it will say the solution is x and y and lambda.
Okay. So for x and y, will like lambda be in the solution?
No. Good question. You should not solve x in terms of lambda. That's not a solution, because lambda is a variable inside the problem. You don't want to answer it in terms of it. There's no lambda here. How could you solve this and say, well, x is equal to 4 lambda? That's not a solution. I don't know what lambda is. You have to say what x is. This should be a number. X and y should be a number. But I thought what you were asking is, do you also have to say what lambda is equal to? Were you asking that?
Yeah.
Yeah. And my answer is, it's actually good if you do. It is good, because it kind of shows that you've fully solved the problem. And sometimes, while lambda doesn't exist in any sort of real sense as a choice variable, it does exist in a shadow. It's called a shadow price. You ever heard this expression, the shadow price? It means it's not really it's a variable which doesn't directly enter your decision-making process, but it is there indirectly and sort of affecting some aspect of your decision process. It's called a shadow variable or shadow price. In this case, you can think of lambda as somehow being, because this is written like a budget constraint, I didn't say this, but this looks an awful lot like a you know, a consumer choice problem, doesn't it? Imagine X and Y are goods. You're deciding how much of X and how much of Y you want to purchase. And the utility that you get from choosing X and Y is equal to X times Y squared. That could be your utility function. I didn't call it a utility function, but certainly you could think of it that way. This is a utility function. X and Y are both goods. And then this could be a budget constraint. This could say that, you know, the price of X is 1, the price of Y is 4, and you have $10 to spend, or 10 units of money to spend. Then this would be a budget constraint, and this would be a utility function, and then this would be a consumer choice problem, even though I didn't call it that. In that case, Lambda has an intuition, which is, how valuable would it be to you if I were to give you an extra $1? That's the interpretation of Lambda. What would you do with it in terms of your utility? Because actually what Lambda does, it's like, you know, it's a multiplier times this constraint, but because the right-hand side is the positive one, if you use this convention, and it's like, well, what if, so if you're thinking of the derivatives in a bit of Lambda, it's like increasing the right-hand side by $1. I don't know how to explain it, but I'm not doing a very good job of explaining it. But it has this intuition of, it's kind of like, on the margin, I'm giving you more money to spend, which allows you to buy more X and more Y, and that'll increase your utility. And Lambda tells you by how much it goes up, sort of. It should be a positive number in this case. Lambda should be positive. I just know that because this is a utility maximization problem. More money is better. Okay, so for part C, this Kaya asked a very practical question, which is, do you need to report X and Y and Lambda? And should any be written in terms of the other? So I have a definitive answer. X and Y should not be written in terms of anything other than just numbers, not lambdas. That I will insist upon. The second question, do I need to report lambda? I'll say no, because it's it's not in the problem, so I won't make you report lambda. But if you do, I would like it. Okay, I answered that question. Yeah, also it might just be a good check for what you're doing. Like if you find lambda equals 0 or negative number, then I think you probably made a mistake. I think. Okay. Or that, or you just didn't follow the convention. That could be it too.
So lambda should be positive.
So I just don't want to confuse you, but if this were a constraint, an inequality here, and then you wrote it the correct way, then yes, lambda should always be positive. But as such, it's sort of an equation, and it doesn't matter if you multiply both sides of an equation by -1, in which case I think lambda could be negative, unless I'm mistaken. The reason I know lambda is positive in this particular problem is because it's a utility, it's a consumer choice problem, and more money is better. So I think it will be positive. But just, don't worry about it. If like, don't think it always has to be positive when you're talking about an equal sign here. When you're talking about an inequality, then it is actually important. It's actually like one of the conditions. One of the first order conditions that we'll find is that, oh, the multipliers have to be either positive or 0. Interestingly enough, they can't be negative, but assuming you've written the constraint the right way, the lambda could be 0 or it could be positive, and it means different things depending on that. This is what we'll talk about, next week, if we have time, and the week after. But for right now, I think you're good to solve problem 2, right? Yeah. Let's see that example. I know I'm taking a lot of time, but let's actually see here. Right? You can see now the screen says solve for S and F. Hope so. Is that okay? Yeah. So from the first order condition, S equals lambda. Let me remind you, that comes from this. All I did was rewrite it, move the lambda this side, I get S equals lambda. That's just something we found. From the second first order condition, we find F equals lambda. Okay, S equals lambda and F equals lambda. Together, this implies that S equals F, right? It's like we're substituting lambda for F into this equation and get S equals F. Okay, so now we know S equals F. Plug this into the third first order condition, which is this one here. If I plug in S equals F into that condition, like here, I'll replace S with F, I think. Yes, I'll replace this S with F. I get M minus F equals 0. That's what I have here. M minus F equals 0. Solve this for F. I get 2F on this side, divide by 2. F equals M over 2. And because I know S equals F, I also know S equals M over 2. So this is that part C. This is the solving of the first order conditions. You get an answer for F and an answer for S. Notice I didn't tell you what lambda is, but it's obvious. Lambda is also equal to M over 2. I think, yeah. Which is interesting, right? If I'm correct, this says how much more utility would a consumer get if I gave them an extra $1? And the answer is, well, it depends on how much money they already have. And in fact, the more money they already have, the more valuable an extra $1 is to them. You know why that's the case? It's a pretty unrealistic utility function, isn't it? It's F times S. This is like saying, like, the benefits of having more food and more shelter really grow really fast as they get more and more, which of course I don't really believe it. And I just chose it for simplicity. Anyways, don't worry about what lambda is equal to. When solving the problem, when like answering your problem, you don't have to worry about what lambda is equal to. Okay, so 3 different methods all got the same solution. And the solution in retrospect is obvious because it just says you'd spend equal parts of your money on food and shelter. And you could have guessed that because of symmetry. Symmetry is a very powerful argument in a lot of mathematics and economics and math for economics. What am I saying by that? If you have 2 variables, just call them X and Y. If X and Y are symmetric in your objective function, and they're symmetric in your constraint, then the only real solution is that X and Y are the same in my solution. Because how could it doesn't even make sense to think that, I could flip the name of X and call it Y, and the name of Y and call it X, and the problem itself hasn't changed. So how could it be better for me to have, more X than Y as opposed to more Y than X? They're totally symmetric. They sort of have to be treated equally in the solution of the problem. So that's it's kind of a shortcut you might want to use at some point, or at least a check on your work. It's nice to have. Comes up a lot in economics. Okay. Guys have any questions about this first basic example of Lagrange multipliers? Seems pretty simple. I think you actually probably need well, let's talk about the general form of Lagrangian, not the specific example, but a more general form, and then another example, and then probably be done with the class for today. Okay, so here's a general form of Lagrangian with 2 choice variables. And like I said, you'll always see optimization problems. This happens to be a maximization. It could be a min. Sometimes it's min, but I just in general use word optimization. It could be either max or min. In this case, it's a max. And X and Y are my choice variables. F which is a function of x and y, is the objective function such that, st is short for such that. And this is a way to write a constraint. That is g, some other function of x and y, not the same as f, but g, some different function, has to be equal to c. That's a sort of generic way of writing the constraint. If that's the case, whenever you see a function, or sorry, whenever you see an optimization problem that looks like this, you can always write a Lagrangian. And interestingly enough, it's the same Lagrangian whether you're doing max or min. You don't have to change. You might say, well, what the heck? How do I know my solution is a max and not a min? Those are the second order conditions, which I do want to teach you about, but I'm not asking you about in the homework. I'll ask you about them on the next homework. How about that? So that's like some caution, right? I'm using the same function whether I'm doing a max problem or a min problem. That means if I really want to know if this is a max or min, I better look at the second order conditions at some point. Okay. You guys get my point though. You can always write this. Just take whatever this f is, put it there, add a lambda, and then take the right side c minus the left side g. And that's the general form. Capital L, sometimes when I'm writing this like on a chalkboard or whiteboard in front of people, one way I designate a Lagrangian function is to write it as a script L. I prefer to use a capital script L to write Lagrangian. And I've seen books that do that too. I've also seen books call it, I think Z. I'm sorry, let me just reference real quick. Yep, wow, I pulled right to it. Holy cow, I'm good, guys. I pulled right to the Lagrange multiplier method. And I have this function here, Z. Wow, that's how familiar I am with this book. Okay, so the Chang Wainwright textbook calls Lagrangian Z. I think the Zader textbook doesn't. It calls it either L or script L. But okay, doesn't matter. Some letter. Okay, I want to show you now for more than 2 choice variables, just so you can see what it would look like. Here's 3 choice variables. Same thing, right? I'm choosing over 3, let's call them X, Y, and Z, whatever the three choice variables are. I have more arguments in my objective function. Of course, I could have more arguments in my constraint as well. Doesn't change at all what the Lagrangian looks like for maximization or minimization. Same looking thing, only with more arguments. So you could do this. You can do this with 3 choice variables if you. Quick question: if you had this problem, how many first order conditions would there be for this Lagrangian? There's 3 choice variables. So how many first order conditions would there be for this Lagrangian?
4.
Yeah, it's 4. You weren't fooled. It is 4 because there's 3 for the choice variables plus 1 for the constraint. I feel like telling you this now, and that is there can be more than 1 constraint in a problem. If there's more than 1 constraint in your problem, you would see it written as such that the blah, blah, blah equals C and blah, blah, blah equals blah. If that's the case, if you see a problem with more than 1 constraint, you can still use this method of Lagrange multipliers. You just create a new multiplier for each constraint. If there's 2 constraints, you use 2 multipliers. If there's 3 constraints, use 3 multipliers. 3 Lagrange multipliers, that is. And you would separate them with little subscripts. So you might say, for the first constraint, you call it lambda 1. For the second constraint, you call it lambda 2, etc. So, if there's a problem with 3 choice variables and 2 constraints, that means the Lagrangian will have 5 variables, and therefore the Lagrangian will have 5 first order conditions, right? And that's true in general for more choice variables and more constraints. In this class, I'm not going to ask you this is the algebra gets more and more complicated as you get more and more variables. So you're solving a larger system of equations. So I really don't think I'll be asking you more than I'll never ask you more than 3 choice variables. If I ever do 3 would be the top. And, you know, I feel it's very unlikely for me to ask you more than 1 constraint. I might do it in sort of the next chapter. Might ask you something with 2 constraints later, but not right now. Okay, here's a review. Step 1, set up the Lagrangian. Step 2, find the first order conditions. Don't forget there's that 1 extra one for the lambda. Step 3, solve this system of first order conditions. Step 4, if required, meaning if I, as the instructor, require you, you may have to look at the second order conditions to ensure that it's indeed a solution to the problem. Maybe. Only do that if I ask you to. Let's look at another example. Consumer choice with asymmetric prices and utility. So, oops, is this the exact same? No, this is very similar to a homework problem too. But I think that one was xy squared, right? That was xy squared. This one's x squared y. Is it really that different? No. And here the prices of x is 1 and the price of y is 4. Oops. But okay. Here the price of x is 5, the price of y is 2, income is 100, and here's a utility function. And this is a problem where I want to see what it looks like when you use Lagrange multipliers. You could use any method. This is not a hard problem. You could solve it other ways, but let's use Lagrange multipliers. We have 20 minutes. You can do it. Let's think about the intuition too. Before we dive into the math, let's use some economics. And says, will the consumer want more X or more Y? What do you guys think? X like is more important in the utility function because however many units of X you purchase, that gets squared, whereas Y doesn't get squared. So X seems to be like, this is a consumer that perhaps has a preference for X, you might say. Preference in the sense that it's a more preferred good than Y, all else equal. It's not symmetric. X squared times Y. So X is something that I like more of than Y. But X is more expensive. X costs $5 per unit. Y only costs $2 per unit. So which of these 2 factors would you guess is more of an important factor in terms of finding the utility maximizing choice of X and Y? Right, let's not forget what this is a problem of. There's the problem. What I've highlighted in blue, that's what I want to do for the next 10 minutes. Solve this problem. What is the utility maximizing choice of X and Y? I'm just asking you right now if anybody out there has any intuition. Do you think the answer will end up being more X or more Y? Any guesses? You can just guess, I don't know.
X, maybe.
You think more X because of the X squared? Is that why you guessed that?
Or the price.
But wait a second. I think maybe your intuition is failing you in this case. I'm sorry, dude. I really like that you said it, but there's something that's going wrong when your intuition. If you think that because the price of X is higher, I would want to buy more X. That's not how prices work, right?
Or maybe Y because it's cheaper.
Okay, so you're switching your answer. You actually think you'd choose more Y.
Maybe.
Okay.
Definitely.
It can't be that you choose more X because it's more expensive. That's not how the consumer choice problem works, because if you're a consumer, you want to get as much as you can out of your money. And if something is more expensive, that makes me less likely to buy it. So
yeah.
So the answer could be Y, and it could be Y because it's got a lower price. Okay, but it could be X too because of this X squared. I mean, if you think of like 10 squared is 100, whereas 5 is only 5, as opposed to 5 squared is only 25, and 10. You know what I mean? Like it's possible without really doing the math. It's possible that saying, well, because this is squared, that's like makes it way more important than Y. And even though X is more expensive than Y, I still want to buy that X because I know whatever I buy will be squared in my utility function. Okay. This isn't that interesting. I'm just saying it's interesting to me to like guess what the answer is going to be, but I'm sure you guys don't care. Well, let's solve it. That's what you should care about is let's get practice using this method. What is the utility maximizing choice of X and Y? And also you'll find this is very, very similar to the homework problem. Okay, step one. You guys want to, do I have the answer? Oh, no, I don't. Yes, this is something we can write together. What's the Lagrangian? Annotate X. What is it? I'll also get you started. L equals, someone just rattle it off to me real quick.
Oh, x squared y
Very good.
plus
Very good.
the, what is it called again?
It's a Greek letter.
Yeah, the Greek letter, lambda or lowercase.
Yes, lambda.
Parentheses,
Mm-hmm.
100
Very
minus
good.
5x minus 2y.
Thanks, Kai. Got it. Nailed it. 100 minus 5x minus 2y. That is what the Lagrangian function is. That's what we're going to want to take the derivatives of. Oh, wow, we can just leave it there. Answer. Oh, this is funny. Okay, so I had the answer on the next slide, but I've also written it there. This is kind of annoying, isn't it? Oops, I already did the first order conditions. That's okay. Here are my drawings. There's the first order condition. I'm giving you the first order condition, which means the one with respect to x. The partial derivative of this whole function with respect to x is going to be what? 2 times xy, because x squared becomes 2x, and multiplying by y, the y remains. Then I'm looking for an x here. I see one here is a -5 and a lambda, so it's -5 lambda equals 0. You see how I get FOC1? As a way to demonstrate to me your understanding, why don't you tell me what FOC2 would be? The one for y.
It'll be 2xy.
Ooh. Nope. Good guess, but no, it's not 2xy.
Or
I'm
x squared.
Yeah, I'm taking the derivative with respect to y, so it's
Yeah.
actually just x squared. Good correction.
Minus 2 lambda.
Very good. Everyone agree with Kai's answer? I agree, and I'm the instructor, so somebody disagrees, that means you think both Kai and I are incorrect. Kai and me? I am incorrect. Okay. And then the third first order condition is almost not worth writing out, but let's do it for posterity. FOC3, you might call it, the one for the Lagrange multiplier. That's just telling me this whole thing here is equal to 0, because there's no lambdas here, and this is all multiplied by lambda, so the derivative of that is simply just 100 minus 5x minus 2y equals 0. Not great handwriting. Is it even called handwriting when you're using a mouse? Maybe it's called mouse writing. It's not good mouse writing. Okay, so those are the 3 first order conditions of this problem. That's it, done with step 2. Let's go into step 3. Guys have any ideas how I might sort of combine these to solve them in a way that works? What do you guys think?
I'm looking at like how to possibly eliminate lambda.
That's a great idea. Eliminate lambda, that's a great idea. Lambda is the thing which appears the least here and here, but not here. So if we can eliminate lambda, it'll look more like a solvable thing. How about from this guy right here? We get x squared minus 2 lambda equals 0. Let's like move the 2 lambda to the other side, and it actually becomes x squared equals 2 lambda, right? Would you agree?
Yeah.
All I did was move that to the other side. Now I can divide by both sides by 2. I don't know if I have enough space here to do that, but you can tell that's what. Hopefully, you can tell that's what I'm trying to do. There, I've just solved for lambda. Lambda equals x squared over 2. That's a 2. It's supposed to be 2. Now I can plug that in for this lambda, and we will have eliminated lambda. That's our goal. That's a good first step. So what will happen here? Let's move the 5 lambda to the other side. And what do I get? 2 times xy, it equals 5 lambda. But instead of lambda, I'm going to replace that with this, which is x squared over 2. So I actually get 5x squared over 2 if I didn't make a mistake. Maybe let's pause here and see if you guys can follow how I got to this point and whether or not you think I made a mistake. I got x squared over 2 from this second first order condition. Remember, x squared minus 2 lambda equals 0. That became x squared equals 2 lambda. That became x squared over 2 equals lambda. So I substituted that in. I got 2xy minus 5 times x squared over 2 equals 0. I moved that to the other side. It looks right to me. Did I make any mistake, or you guys agree with how I got this?
I agree.
Okay, I got it by exactly what Kai said, which was let's eliminate lambda. It was exactly the right suggestion because lambda was the easiest thing to get rid of. Why not do it? And that left us with this. What's going on here? Well, I almost have solved for y, if you noticed. Pretty close. Let's observe that there are x's on both sides, which appear as multipliers of the entirety of the left and right side, which would lead us to think we could just eliminate, divide both sides by x, and the equation it holds. There's one caveat to that, which is you need to consider the possibility that x could be 0. If x is 0, you shouldn't divide by 0. So you can really only do this if x is not 0. And another way to say that is, if x is 0, then this equation holds. If x equals 0, then this equation holds. If x is not 0, then we can divide by this, everything. So let's do that. Let's think of this as being either x equals 0, or we get to the equation. I'm now dividing x from both sides. 2y equals 5x over 2. That looks right to me. I want to solve for y equals something. So let's divide both sides by 2. And then this becomes actually 5x over 4. 5x over 4. Okay. So what have I learned so far? That either x is equal to 0 or y is equal to 5x over 4.
Do we have to write, like, make that clear, like when we're answering like the homework?
We have to make what clear? That x could be 0?
Yeah, that y will hold if x like is greater than 0.
Well, you know, for mathematical correctness, you should put that in. Even though, so now let's think about economics. The economic intuition should tell you x will never be equal to 0. Can you guess why? How do I know that x will never be equal to 0? In a solution. Just here, let me rephrase the question. How can you be sure? There's an easy way, but to tell me, how can you be sure that a consumer who's trying to maximize their utility would never choose x equals 0? Remember what their utility function is? X squared times y. What happens if they choose x equals 0? They get a utility of 0. No matter what y is, their utility will be 0. Agree?
Yeah.
So you can eliminate this not using math, but using economics. I mean, essentially economics is math. You go back, you can go more fundamental. So of course the math works out too. When the objective function is 0 and in other parts the objective function is positive, that can't be the maximum. So we can actually just eliminate this possibility that x equals 0. If for some reason you didn't have that intuition and you weren't sure, just put it in there, say either x equals 0 or, and then continue. with the assumption that x is not 0. Does that help?
Yeah.
Yeah.
So if we know that x can't be 0, we have that intuition.
Yeah, you know what?
Do you still want us to write it down?
I would like you to write that down. Like when you're going from this line to this line of algebra to this line of algebra, just put a little note that says x can't be 0 because the utility would be 0, comma, and then just go on from there with the assumption that x is not 0. Okay. And that's why you can divide it from both sides and simplify it to this equation here, y equals 5x over 4. We're still not done though. We want to solve this problem for x and y. How can we do that? Well, the third first order condition, we haven't used that one yet. We should use that one. It's 100 minus 5x minus 2y equals 0. I can plug y equals 5x into there, and we'll have only x's, and we can solve for x. What will happen when we do that? Do I have any space here? Can I use up this space like up in the top left? From FOC3, I'm going to get this equation: 100 minus 5x. Now I have minus 2y, but I'm replacing y with 5x over 4. So 2 times 5x over 4 is actually 10 over 4 or 5 over 2x. So minus 5 over 2x, 2.5x equals 0. This should be pretty easy to solve. Negative 5 minus 5 halves, that's, what do you want to say, 15 halves. Move that to the other side, you get 100 equals 15 over 2x. 15x over 2, better way to say it. 15 halves x. And now multiply both sides by 2/15, I get what, something like 200 over 15 is my answer for x. I don't even know what that is. I'm going to give it a little star though as an indicator that we believe that this is the solution for x. Why do we believe it's the solution? Well, the only other possible solution would have been this x equals 0. And we already eliminated that as a possibility because that gives you a utility of 0. So we really think x star is probably 200 over 15. You'd also want to find y star. The solution for y is going to be equal to whatever that times 5 divided by 4 is. That's not pleasant. What is 200 divided by 4? It's 50. And so I'll put that as the numerator. And this 15 is going to be cancel out with this 5, and it's going to be only a 3. I think that's what I get. Y star equals 50 over 3. X star equals 20 over 15. Does this seem right? Did anybody do this on their own, get the same answer?
Yeah, I got the same thing.
Oh, great. I mean, I have the answer on my next slides too, so when I scroll down, you'll be able to see my answer. But I want to see how we got it all on this one screen, sort of jumping around a little bit because I didn't have all the space I wanted. But I just wanted you to see from this first order condition, second, third, these 3 first order conditions, that was enough. That was enough to find x star and y star. How did we do it? We took Kai's great suggestion to first eliminate lambda. Once we eliminated lambda, we had a pretty simple equation here of x and y, and we plugged that into this constraint first order condition, or the Lagrange multiplier one, and kind of went from there, solve for x and solve for y. And this method is pretty useful. I think it will get you an answer most of the time. It will definitely get you an answer in the homework problem I gave you. You do this. What's the difference there? The difference in the homework is that the squared is on the y instead of the x, and that these numbers are different. But other than that, it's exactly the same problem. You can use exactly the same method to solve it. I want you to, in fact. It'll be good practice. You know, it'll be good practice for this sort of simple form of the method of Lagrange multipliers so that in future classes, we can talk about even more complicated types. So it's sort of deliberate. I asked you to do that, do next class, so that starting next class, we can talk about even more complicated. Yeah, let's look at, get some any questions about this. I'm going to clear my drawings. Speak now or forever hold your peace. Okay. Here it is. Oh, I forgot to, I had this in here as like, is that all of them? Nope, there's a third one. Okay, so here are the three. This is the same thing we did, only written out. I used a slightly different method here. I sort of solved for lambda, both cases, and then I set them equal to each other. That's another way to eliminate lambda. You simplify this to get y equals f. Wow, I was a little remiss here by, I just used the word simplify, but not only am I simplifying this, I'm tacitly assuming that x is not equal to 0. And rather than tacitly assuming that, I would rather you explicitly write it to say, oh, you know, x is not equal to 0 because of the utility function. Therefore, we can simplify it to get this. We can plug that back into the third one to get this. Yeah, this looks like the same answers, doesn't it? Oh, I had 200 over 15, but I guess that simplifies to 40 over 3. And then y is 50 over 3. So let's think about this intuition question. Should we buy more x or y? We buy more y. I think that's what you thought, Kai, actually. Once I reminded you about this effect of the prices, was that, yeah, the price effect would dominate the squared utility effect. And that's true. In this case, I end up purchasing more of good y than of good x, even though this good x amount is squared. You might think, what the heck, isn't that a bigger effect? The fact that you can square this number, 40 over third. Here's the kicker, and you sort of built into the problem is that every time you get a larger x and you get x squared, that also makes you want to have more y, doesn't it? Because whatever you choose for y, you're now multiplying that times x squared. So, you know, that's built into this problem when you talk about the partial derivatives, etc. That's, you know, one way to think about why you have more y. You guys have any questions? I think this is the end. Oh. Therefore, we found a potential solution to this consumer choice problem, x equals 40 thirds and y equals 50 thirds. Is it actually a solution? What do you think about that? Is this actually the solution? I think it is. You guys can doubt it if you want. The answer is yes, because the corner solutions and the budget line are clearly worse. There must be a max somewhere, and this is the only possible one. When I say corner solutions, what do I mean? I'm talking about these cases here where x could be equal to 0 or y could be equal to 0. And you even see that in the math. I sort of glossed over it here, but in the slides, I didn't spend any time talking about, wait, what if x is equal to 0, y equals equal to 0? But I'm addressing that exact same issue here by talking about corner solutions. The corner solutions on the budget line are clearly worse because they give you a utility of 0. There has to be a maximum somewhere. Somewhere on the budget line, you have some utility that maximizes you have some choice which maximizes your utility. And this is the only one. This is the only possible one. X equals 40 thirds and y equals 50 thirds. So it's the answer. If you wanted a more formal solution, look at the second order conditions, which I haven't told you yet. And I'm out of time, so I'm not going to tell you today. But we'll talk about it next class. How about that? Yeah. Oh, here's a preview. Do you want to look at it, or is like it's too hideous? You don't even want to look at it. Get it away from me. This is what it is. It's going to look like this. It looks like the Hessian matrix, only more complicated because you add a row and add a column to it. Okay. So we'll talk about this next class. You don't need it for the homework. So. Stop share. You guys feel good on the homework? You'll be fine. Email me if you have any questions, but I think you'll be fine. Okay, guys. I think that's it. I'll see you Tuesday.